Okay, don't worry. I'll let you know when we're live. Okay, now we're live now. All right. Well, thank you very much for being here. Now we're gonna have a second talk of this section, which is gonna be delivered by Professor Eduardo Inacio Duzzioni. He holds a bachelor's degree in physics from the Federal University of Santa Catarina, a master's in physics from the Federal University of Santa Catarina, as well as a PhD from the Federal University of Sao Carlos, as well as a postdoctorate from the Federal University of ABC. He's currently a professor of physics at the Department of Physics of the Federal University of Santa Catarina, as well as the CTO of Quant by Quantum Computing. And Eduardo's talk is entitled Quantum Algorithms to Solve Fluid Dynamics Problems. Be welcome, Eduardo. Thank you very much. Over to you.
Okay, thank you. First of all, I'd like to thank the organizers for this opportunity. That's a very important event in Latin America. I believe that from now on, we are in the map in the quantum computing. Okay, so thank you, Araceli, Salvador, etc., and the others. Thank you. Okay, today I'll talk about quantum algorithms to solve fluid dynamic problems, basically using quantum annealers. The collaborators in this work are Giovanni Polacchini, Caio Góes, Thiago Maciel, Rafael Cuenca, and Juan Pablo Salazar. As you can see, this is a team with different skills. We have mathematicians, physicists, and also engineers. In some of my talk here, I will talk first, I will show you where we live and what we do. I will tell you how the quantum annealing works and how to use the quantum annealing to solve linear least square problems. And as application of this technique, I will solve two problems, two differential equations. One of them is the heat equation in a two-dimensional plate, and then I will solve the one-dimensional Burger's equation, but here using a different method based on machine learning. And then I will present the conclusions and perspectives of this work. Well, I live in the south of Brazil, in the Santa Catarina state, more specifically in the Florianópolis island. Here is a very beautiful place. On the left side, you can see here the pictures of the campus of the Federal University of Santa Catarina in Florianópolis City. It's a very nice place. But as I live in an island, there are a lot of beaches, very beautiful places. So you are welcome to visit us here, okay? I also a member of two research groups, the Southern Quantum Information Group. You can visit our website here. And also I'm a member of the Quantum Computing Group, also in the Federal University of Santa Catarina, and you can visit us here. And as mentioned, I am also CTO of the Quantum Computing. In this startup, we develop solutions for quantum algorithms and also post-quantum cryptography. Well, now I'll start talking about the technical things. Basically, I'll explain how the quantum annealing works. Well, the quantum annealing is an heuristic search algorithm to find the lost value in the energy landscape. I mean, this picture here, you can see the energy landscape, and you want to go here. That is the lost value. But there are different ways to arrive there. You can arrive there using classical techniques like the simulated annealing. Simulated annealing use classical fluctuations based on the temperature to jump these hills, okay, and finally arrive the valley. But there are other possibilities. In one of these possibilities is using the quantum mechanics. In the quantum world, the basic idea is to use quantum resources, in the case, the quantum fluctuations. In this case, the particle does not jump the hill, but it tunnels the hill, okay? And as shown by Kadawaki and Hishimori, this is an efficient way to solve these problems. Okay, although it's a very hard problem. But how to implement that in practice? Okay, the basic idea is to start from the ground state of an easy to prepare Hamiltonian, H0, that is a sum of Pauli matrices aligned along the x direction. And you evolve the system in a such way that there is no transition between the ground and the first excited state. So that at the end of the evolution, this is an adiabatic evolution, you arrive to a final Hamiltonian that is the easy Hamiltonian. This kind of Hamiltonian is important because it's possible to map several problems in this kind of Hamiltonian, and we do that by adjusting the coefficients alpha and beta in order to encode the solution to your desired problem. So the adiabatic evolution can be performed in different ways, but one of them is through this way, where f is the schedule function. Okay? In this case, f is a function of the dimensionless time, that is t, the current time, over the capital time, that's the total time of the evolution. So the basic idea of this model is start from the ground state and arrive to a desired solution in also the ground state of the final Hamiltonian. However, it's important to remember that in the real world, we are not at 0 Kelvin. You are in a non-null temperature, so you are not in exactly the ground state. That's the why quantum annealing needs to do a lot of samples to obtain possible solutions to or approximate solutions to our desired problem. Then the basic idea here is to use the quantum annealing techniques to solve linear least square problems. Well, the solution of linear least square problems is the solution of the linear system of equations. Suppose that A is a matrix n by n, B is a given vector, so A and B are given, and our problem here is to discover x. It's possible to map this problem into the Hamiltonian problem in this way, and we observe that here that if you know the correct solution of the system of coupled linear equations x, then this value will be 0. So the ground state of this quadratic Hamiltonian is 0. Therefore, you solve your problem. Okay, that's the way we do to encode this kind of problem in a quadratic Hamiltonian. But I mentioned before that we use the Ising Hamiltonian to solve problems. And the question is, how can I map this Hamiltonian to the Ising problem? The strategy is the following. Each component of the vector x, each component xi, that will be represented using floating point notation in this way. Okay, you can see here that Q is the bit that can be values 0 or 1 times power of 2, the binary representation. Capital R is the total number of bits used in this representation. And these constants, these values C and D, are used to enlarge the interval in which each component xi can be represented. That's the basic idea. Then, if we substitute the xi in that quadratic Hamiltonian, we get this new Hamiltonian that have these new parameters a and b. Okay, we notice that these new parameters depend on the matrix coefficients a, also c and d that determine the interval of representation of each component xi, and also the components of the vector b. But here we note this is not exactly the Ising Hamiltonian, because for each variable Q, that is the bit, is indexed by 2 indexes instead of just one, as in the Ising Hamiltonian. So to do that, it's necessary to do a mapping between these 2 indexes, I and R, to a new index L that is performed in this way. Okay. Remember that capital R is the total number of bits used in the floating point notation. It's possible to do an inverse mapping in this way, where here is the floor function and modular function. So we finally found this new Hamiltonian. We observe that this Hamiltonian is very similar to the Ising one, and this Hamiltonian is called quadratic and constrained binary optimization, a tubular Hamiltonian, okay, because it's solving quadratic problems. And the last procedure here is the quantization of these variables. Instead of have bits, now we have qubits, okay? And they have this property. So the eigenvalues of these operators are 0 or 1. And it's possible to do a map connecting these quantities Q and Pauli matrices in this way. Then you connect the cubo Hamiltonian to Ising Hamiltonian. Now we have all the background necessary to deal with our problems of interest. The first problem, that is how to solve the two-dimensional heat equation using this approach, using quantum annealers. In general, quantum annealers are used to solve optimization, binary optimization problems, although now they are using for discretizing also, more general just than binary, okay? And here you are using for continuum variables, okay? So this is the heat equation in the stationary regime for a square plate size of length L with multiple heat sources and sinks. This is the equation, and these are the boundary conditions. Okay. So our goal here is to discover the temperature in each point of our plate. You can find this work following this archive code. Well, the first task here is to discretize our spatial domain, which means that our derivatives can be written in a discrete way, in this way. There are higher orders that will be neglected here. And the physical system we are considering is this plate with size L. And we split this domain in 11 small cells along the X and Y directions. The cells here are the boundary conditions. However, the unknown values of the temperatures are inside this square. In this case, we have 81 small cells. I mean, 81 variables, 81 values of temperatures that we don't know. Okay, and through these two equations here, we return to the heat equation, and you get this system of linear equations. So our goal here is to solve the system of coupled linear equations. This is a very well-known procedure used mainly in computational fluid dynamics. Okay, and we are using here is a standard procedure. The novelty here is that we are using a quantum computing to solve the system of linear equations. Okay, that's our contribution here, basically. Well, but it's important to note that if you have too many variables, it's sometimes hard to embed these variables in the D-Wave quantum computers, for instance. Why? Because if you have many variables, you need a lot of connections. And one of the main problems today in the D-Wave quantum computers is the connectivity. That's why we decided to split that big system of linear equations into smaller ones. We do that using the Gauss-Seidel method. In this method, we basically, I will give a simple example here. We basically split the system of linear equations in two parts, as you can see here, and you have these two equations. Suppose that initially you do a guess for x2 and you find the value of x1. We replace the value of x1 in this equation below, and you find a new value of x2. And then we replace this new value of x2 in the above equation, and so on. Then we are solving the system of linear equations iteratively. That's the strategy you use here. Why? Because now you need to solve smaller systems of linear equations. Okay, that's the idea. So we split the system with 81 variables in 9 smaller blocks. Okay, and the results that we are finding using this approach are here. In the vertical axis here, we plot the relative error as function of the number of iterations. The relative error is defined as the difference between the solution after k steps and the exact solution. This exact solution was obtained numerically in a classical computer. This was done in order to benchmark the quantum computers and the 2000Q and advanced systems built by D-Wave quantum systems. Okay, and the results are here. Okay, the classical solution is the blue line. This solution was obtained using the classical Gauss-Seidel method, and we observed that the relative errors obtained by quantum computers are in general greater than in the classical case. The curves in red are obtained in the 2000Q QPU, while the green curves were obtained using the advantage QPU. Okay, we observe that the advantage here is a bit better than the 2000Q QPU, but it's important to observe that after 6 iterations here, the quantum computer goes to a stationary value of the relative error, while the classical Gauss-Seidel keep going to smaller errors. And we believe that this is because we are using a limited number of qubits in the precision. In this case, we use 3, 5, and 7 qubits of precision to obtain these solutions, while in the classical case, we use the double precision of classical computers. Okay, but the question is it possible to overcome this problem here obtained by the quantum machines? The answer is yes. Our strategy here, observe that the same quantities in this picture. The idea here is to shrink the interval in which the components xi are calculated. After each step of the iteration process, there is a factor, a shrink factor, gamma, that's 0.8 here. So after each step, the interval in which the variable xy is searched is every time shrinking. And we find that taking into account this procedure, in both classical and quantum solutions, we observe that the quantum solution was improved a lot here, as you can see, even obtaining in some cases better solutions than when compared to the classical Gauss-Seidel method. So this is exciting, although it's not exactly clear why this quantum solution is better, since in the quantum case you are limited to 3, 5, and 7 cubes of precision, while in the classical case we are using double precision of a classical machine. Okay. And okay, finally, just to show you our solution to the profile of temperature in this plate, in this square plate, you can see this distribution of temperatures. Okay. If you want to see more results about this work, you can look for this paper in arXiv. Okay. Now I will move to another work. In this work, we are using also quantum annealers to solve partial differential equations. However, using a different technique that is using in machine learning, the regression in supervised machine learning. Okay, so the general problem we are considering here is the solution of a partial differential equation in this way. This partial differential equation L here contains its partial derivatives and other terms. Okay, this is the initial condition, and this last equation is the boundary condition. Okay, with these three equations, we are able to define the problem we need to solve in partial differential equations. But what is the strategy you need to employ to solve this problem using machine learning? Well, the basic idea developed by these two guys here is, okay, let us build a loss function in this way. Observe that this loss function is a sum of positive terms, quadratic terms, okay? And observe that they are obtained through each of these equations here, the first equation, the second, and the third one, with the difference that in the minimization process, we change U, the solution of the partial differential equation, but by another function f. Observe that this function f is function of x and t, but it also needs another parameter. This parameter that it is a set of parameters used in neural networks to obtain this fit. Okay. And our strategy here, we use the boosting machine learning technique. This technique is based on the following question. Can a set of weak learners create a single strong learner? Okay, I mean, if you have neural networks that we are calling weak learner that have small numbers of neurons or layers, but if you perform a weighted sum of them, and it's possible to find a stronger learner, I mean a stronger neural network to solve our problem. That's the basic idea. So our task here is to find these weights W, W1, W2, etc., and so on. Okay, that's our task here. So, okay, so let's answer the following question. How to fit the function f of x? I will use here this expression. Wk is the weights, is the weight used in the previous slides. They are the weights of the ensemble, while hk of x is the result of the k-weak learner. Okay. So our work here to find the value of x is to minimize this quantity here, where the first term means the error in M training sets. We are performing an average over M training sets. Here, XM and YM are input data. Suppose that X and T in our partial differential equation are position and time. XM is position and time in this case. and ym here is the value of the solution of the partial equation for this point xn. Okay, that is.
Excuse me, Carlo. Sorry, 2 minutes left.
2 minutes. Okay, so that's our idea, and this term here is the regularization term. It's used to avoid overfitting. So our task here is to develop a quantum version of the Boost machine learning, that we mean QBoost for regression problems. We are also invoked the condition that the sum of the weights is equal 1, and again we use the floating point representation, and we obtain this very complicated Hamiltonian, in which QL and QL prime I are operators. Okay. So to solve the one-dimensional Burger's equation through QBoost, we will deal with this problem where V is the viscosity and U is the fluid velocity. Okay, these are boundary conditions and initial conditions. The advantage of using the Burger's equations in one dimension because it has analytical solutions, so it's very easy to get values of U to train our neural networks, and the values we have used to train our classical neural networks are these values. One, here are the number of neurons in 1, 2, 3, 4, 5 layers in each neural network. The value of the loss function for this neural network is this one, and so on. Time over number of epochs is here, and number of neurons times number of layers is here. Our results using the D-Wave quantum computers are here. Here in the vertical axis, the variable U, the solution of the Burger's equation, and here in the x-axis is the position, and while different colors indicate different times in which the solution is obtained. This first picture shows the exact solver, that the exact solution of the cube Hamiltonian. And this is the solution obtained through simulated annealing. That's the classical solution using the annealing. And the quantum solution is here. You can see that they are very similar, but if you go into the details, it's possible to see that the quantum solution is better than the other ones. Okay, this is just a table to show you our results and simulation times. We see that the exact solver have limitations due to the number of qubits since the memory increases exponentially, and the simulated annealing here. But it's important to pay attention here to the best result to the problem that's obtained through the quantum annealing. Okay, just to finish here, this picture shows that when you compare the result obtained by the QBoost compared to the best weak learner, this is the value of the loss function along the y-axis. The best weak learner is this line. In the training and test set, we observe that except for number of precision cubes 3, all other solutions obtained in the quantum case are better than the best weak learner. I mean, the QBoost is giving us good results. Okay, and it's also important that the fundamental, the ground state is here, and these other points means excited states. So you are sampling other excited states, and they are giving better solution than the best weak learner could give us. Okay, just finish to show you how to solve partial differential equation using quantum annealers. We use different methods. One of these methods is the discretization method, and the other one is the boosting. We implemented in both methods using 2000 Q advantage quantum process units. We observed that in both example, two-dimensional heat equation, one-dimensional Burger's equation, that quantum computers have good solutions and in some cases even better than the classical solution. And it's important to observe that the bottleneck of these implementations relies on the connectivity, the limited connectivity in these computers. But in some cases, mainly when we are working with sparse matrices, maybe we can achieve better results than the classical computers, classical machines. And another possibility would be developing specific topologies to deal with particular problems. Okay, thank you for your attention.
Thank you very much, Eduardo. It's been a pleasure to listen to your presentation. Thanks a lot for sharing your knowledge and research results with all of us. Okay, so we'll be back in a sec for the next presentation.